here, make sure I'm actually hitting record, is obviously all of the formulas that we've gone through and have utilized in the class as of so far. So effectively, it's more of just making sure that we're, essentially using the units appropriately as we're going on through. I obviously like to refer to it as thinking in units. So, and that's why there's that lecture online that you guys can also watch as kind of another example for you. So you have an easier way of kind of going through it and seeing what's what. So I'm still getting my wonderful screens ready to go so I can see everything that's going on. Okay. So first up, this is just going to be the general distance formula. Hence we've got y, the y could be an x. Don't worry about it, whatever works for you. Initial velocity is the v sub o multiplied by time. Now this is plus 1/2 of multiplied by the acceleration multiplied by time squared. So in the case of when we're normally working, where we have gravity, which is at 9.81 meters per second squared, this is a negative 9.81. So it makes this right here naturally a subtract 1/2 times 9.81 times time squared, because if we multiply two positive numbers by a negative number, we get a negative number. Okay, and then plus or minus, you see that term, the y sub 0, so the initial starting position. So this can be positive because we're starting further off the ground and we're falling down to it, or we can be starting from a lower position and trying to throw an object up to it. Hence why we need to always make sure we're paying attention to the units and how things are going through. Now, the velocity formula is velocity equals our initial velocity. Now, you see here, this says minus gravity times time, but in reality, this could be another situation where we have effectively that it should be really a plus sign times whatever acceleration we're using. So obviously that can be modified depending on whatever situation we're at. And then I'll just go ahead and drop that in there. So it makes it pretty obvious of where we're going to be doing some multiplication. Okay, next one is kinetic energy equals 1/2 multiplied by the mass multiplied by the velocity squared. And then our potential energy is going to be our mass multiplied by whatever that force of gravity happens to be in that situation, multiplied by the height in meters that object is going to go ahead and be off of the ground. Now, strain is going to be that 1/2 multiplied by our volume. So obviously the size of the object multiplied by the stress and the strain. Okay, yeah, no worries. We'll work our way through those once we get through here. Pressure equals the force, remember force equals mass times acceleration, divided by the area that it happens to be obviously being placed upon. And then good old force equals our mass times our acceleration. Now remember, we always have the constant acceleration on Earth of just good old gravity, but we can have other accelerations from obviously the mechanical work of muscles shortening and the body moving through space. Friction is going to equal the coefficient of friction multiplied by the normal force, and the normal force is going to be the force that's going straight down into that object. So if we happen to be working with something that is on a plane, now the normal force is just that pen being pulled straight down. So as I'm tilting it, it's actually going to have effectively still that force going down, but now it's the force going down into the platform. And we now have part of that force vector that's pulling the pen laterally. So at some point, the pen naturally is going to slide. It's actually stuck on that thing. So if I had it here instead, and then from there, you would actually be able to figure out using good old trig where effectively what the coefficient of friction is between those two surfaces. Now, work is the force multiplied by the meters that it's going to go ahead and move the object. This is our basic leverage where our resistance times our resistance arm equals our force times our force arm. But in reality, what I should drop in here is a sigma, because that is going to be the sum of each of those. So, and what we want is Greek. because that's going to be the sum of all multiplied by the. Okay, be a little cranky. Multiplied by the sum of all those. Power is simply going to be our work divided by time. So let me just go ahead and change that to T, as well as our impulse is our change in force multiplied by our change in time. Now, momentum equals our mass times our velocity. And then obviously we've got our gravity. Now, when it comes to angular motion, everything you guys need is going to be between this corner over here and this corner over here, okay? So our moment of inertia equals, let's see, I equals our mass times K, and K, remember, is our radius, so it's going to be that radius squared. Our torque is going to equal our force times the distance it's going to be from the actual fulcrum in a parallel component. That's why you see that upside down T there. Angular momentum, the H is going to equal to our mass times our radius squared times our angular velocity. And then angular impulse equals our torque, force times distance, times time. That's going to be being applied. So if we want to figure out, obviously, how much torque is required to accelerate an object with a certain inertia, simply there's what we're doing mathematically, which breaks down naturally to the mass times the radius squared times acceleration. Now, this is going to be for centripetal force, where it's going to be equal to either of these two options, where it's the mass times the velocity squared divided by its radius, or the mass times the radius multiplied by our rotational velocity squared. And then what we have here is obviously our basic trigonometry in case we need that, along with quadratic formula, which is useful when we're doing our distance formula. However, we obviously have to solve for time, where we'd have acceleration and the initial velocity. And hopefully from there, we know what we're going to be solving for our distance. Okay, so give me a second and I will pull up those questions and we'll work our way through them. All right. All right, folks. So question is this. Okay. Can everybody read what I've got up here? Okay. So we're increasing the torque on the ACL. Athlete is squatting 250 kilograms and weighs 100 kilograms. ACL can take 500 newtons of force. how many degrees of internal rotation can they have before the ACL tears? Okay, so if we're going to go ahead and now, let's go ahead and when in doubt, draw it out. Okay, so if we're thinking about their legs when they're squatting, instead of their legs being straight down like this, we're thinking about their knees are going to be knocking in, internal rotation. Not a good position to be in when we're squatting really heavy weights above us. So effectively, when we're straight up and down like so, our angle here effectively is far of internal rotation is going to be really 0. And then if we were all the way essentially flopped in completely somehow, that would be at a perfect 90 degrees. And we're probably going to blow it somewhere in between. So we know that altogether, this person is going to go ahead and have 250 kgs on their back, and they weigh 100 kgs. Okay. We go to Snap City at 500 newtons through the knee. Now, we don't have the lever lengths and otherwise, so the best thing we have to do is try to equate, okay, based if we were just figuring as every degree we shift, what would be the point of which it's going to blow? Well, the first thing we need is just to get everything into newtons. So we need to take effectively 350 because it's the system mass. It's both the weight of their body and the weight of the bar on their back, and multiply that by gravity. So we can also get that into a force that effectively is newtons. Because the way it's currently set up, we don't actually have a force yet. We just have effectively a amount of newtons. So we're going to take 350, multiply that by 9.81, and then we have effectively 3,433.5 newtons. So now, as we're going to be rotating, we're going to be increasing that force that's occurring. So what this effectively means is as we keep rotating from being straight up and down to being inward, at some point, that force is going to cause that to rupture. So that twisting motion that's obviously occurring at the knee at some point is going to overwhelm it, which means we need to essentially look at what's going to be the sine of the angle. And is the key. And really, all we're looking at there is trying to figure out, okay, well, as the knee keeps internally rotating, it's going to happen at some point. So literally, sine of the angle is going to be equal to, and so we've got our hypotenuse and we have our effective opposite, so to speak, as we're going on through that angle. So really, we just are going to have so that overall answer is going to give us what we're looking for. So what we're really looking at there, and I'll switch back so you can see my actual grading criteria, is you essentially are doing the trig to figure out the force and move on. So really, I was looking for you guys to write out something along those lines of showing that you guys were thinking through effectively how you'd come up with that sum. So the next question that was meant to be, pretty hard. Okay. holding yourself at the top of the push-up with your own body weight. If you hold yourself up with one hand and you are supporting in approximately 70% of your body weight with it, how much force is your hand supporting? Okay, so this is pretty easy. You're literally just going to take your body weight and then multiply that by 0.7 because it's 70% of your body mass. And notice it's force though, so we need to multiply that by 9.81 meters per second squared. That was it for the first part, okay? You're resisting with your core, the rotation of your body, which is the width of your shoulder to your spine. So effectively the radius from your shoulder to your spine. Estimate this as 15% of your height. What is the torque required by your core to keep from rotating? Okay. So effectively, all we needed to do is take, and we've got our force from above. Okay. So we're going to take that force, and then we're going to multiply that by your height times 0.15, 15%, equals the torque required right here. So then, the angle for your triceps to keep you supported at the top is 89 degrees. Your form is 20% of your height. How much force does it take if the level arm is only, oh God, lever arm is only 0.5 centimeters long for both parts? Okay. So notice we've got form, and we're going to have the lever arm for effectively your triceps. So tricep force is what we're solving for, multiplied by 0.5 centimeters. And remember, well, it's going to be, we're then going to have to do the mathematical of take that tricep force multiplied by the sine of 89 equals actual force from the triceps. And on the other side of this, okay, so we've got that, the force side of it, which is going to be your body weight times 0.7 times 9.81 meters per second squared. So we're not losing our units. Multiplied by the length of your form, which is going to be your height times 0.2. And then once we factor all that through, you're good to go. Yeah, it's really complicated. But the idea is it's more about, can you set this up by using logic, working your way through the formula as to what's going on. Yeah, no, guys, yeah, it can obviously be quite intimidating, but the goal is, like I said, take your time, work your way through it, one piece at a time. Any other questions, comments, concerns that I can go ahead and work through for you guys?
I was just wondering about the lab 4 that was actually due this morning. I tried to look for the videos, but I couldn't really find them. Like nowhere.
Okay. All right, so lab 4.
It's like I looked on Blackboard and on the YouTube and all the playlists and stuff, but I could find like the force plate videos, but that's not what the assignment is about.
Okay. Give me one moment. That's unfortunate. All right, so now this lab that you guys were just supposed to do, that was the center of gravity lab, right? Okay. And this is also where you're going to see, the postural sway and the isometric clean pull. But if you guys are wanting to, you can still come by the lab and do the clean pull. The postural sway, we're going to have to rig it up a little bit more, but we'll be able to mathematically derive it because our other force plate is currently being utilized for research over in forensic science. Doing a little collaboration over there. So what other questions would you guys like to review upon? Okay, 26 on the study guide. Okay. So force required for a deltoid that inserts 5 centimeters down a 0.751 meter arm. So make sure right there you don't lose the fact that these numbers are different. So this deltoid, we need to put in 0.05 meters whenever we enter it in. Weighs 5 kilograms, moment of inertia is at 60% of its length from the shoulder joint, and the arm is being held perpendicular to the floor. So straight out. Deltoid attaches at a 10-degree angle. Okay, smallest angle towards the shoulder, force in newtons. So we're setting up our vertical force is going to be multiplied by the length of that lever arm, 0.05, which is going to equal our 5 kilogram load for the arm multiplied by gravity, so 9.81 G. And then we're going to multiply that by essentially the length of the arm, which is 0.751. And from there, the 0.6, because remember, its moment of inertia is at 60% of its length. So then our vertical force is going to be divided by our delta force, and that is going to be the sine, or equal to the sine of 10 degrees. So this initial value is going to be equal to 442.0386. So then from here, because we've got the vert force, remember we're going to cross multiply and divide. So now we're going to have our delt force equals that vert force of 442.0386 divided by sine 10 degrees. So the delt force overall is going to be equal to, okay, 2,545.59. Okay, you don't need to do all that significant figures. Saying it's about this, or 0.6 is more than 5. All right, what are the questions you guys want to go through? All right. So where's the force need to be produced on a lever? If it is a resistance arm of 1 meter, 20 kilograms of resistance, and the force produced is 100 kilograms to keep this in place. Okay, so we've got 20 kg multiplied by 9.81, then multiplied by 1. So on the other side, we're going to have 100 kg times 9.81 times question mark. So effectively, this distance, we'll call this x, needs to balance out in such a way that we're going to obviously have this where it needs to be in a balance. So if we come over and we're going to have 20 times 9.8, actually we can get rid of the 9.81 off both sides because it's on both sides. So let's just go ahead and simplify this to 20 times 1 equals 100 times x. So if we divide both sides by 20, so we have 1 equals essentially 5 times x. Well, now we're going to divide both sides by 5. And also, just to kind of help a little bit, if you're thinking about setting this one up, it's going to look effectively like this, where we know we've got that 20 kg weight over here. It's at 1 meter away, and then we've got our fulcrum. Then we're wondering how long this fulcrum needs to be because we have a 100 kilogram weight. We're going to go ahead and set down on that side. So that's what we're trying to solve for, is where on the dotted line when we place the weight. What other questions you guys want to work your way through? Yeah. Now, if it just said producing lever, if it has a lever arm of 1 kilogram and the 20 kg is at the far end, that's a different math problem entirely. But it's actually still going to be relatively similar. It's going to be effectively, it'll be in sixth because you have to have a 1 to 5 ratio of the lever arm. So that would literally be, instead of 1/5, the answer here would be 1/6. So you put the fulcrum in at 1/6 the length, keeping it obviously far closer to the actual mass. Well, let's go and look that up real fast while we're talking with you guys. Lab 5 is meant to be due on week 14. So if I go to the actual assignments tab, pull up that bad boy, it is due on the 22nd. Thank you, Colton. Number 20. So what is the angular acceleration? If it starts rotating at 13 degrees per second and increases to 18 degrees per second in 10 seconds, it has a radius of 1 meter and mass of 10 kilograms. Now remember, angular acceleration is simply going to be equal to our final velocity minus our initial velocity divided by time. So effectively, it's just 0.5 degrees per second. And then since we're here, remember angular inertia, because we just went through our wonderful formula. So give me a second, I'll just bring that back up real fast. Anytime, bud. So our inertia right here is our mass times our radius squared. So in this example, it's literally going to be so any other questions you guys have right now that you'd like me to go ahead and work through? Yeah. trying to think. I think it's actually one of the questions on the review. Oh, I guess, yeah, vortexes. Okay, so one moment. Okay, so with Magnus effect, what we do is, due to the rotation of an object, we're creating higher pressure and lower pressure on two different sides of the object, which is going to cause that essentially object to start to curve into that direction. So in fact, actually, after giving the lecture, I went and found this happy little image to make things a little bit easier for folks to go ahead and visualize, where effectively, because we're slowing down the air on one side, because we're effectively pushing against and we're going faster in the other, in turn, it's going to create a bit of a vacuum, which in this example is going to shove the ball down. In fact, this is the basic idea of throwing something like a fork ball. Because you can see this is how pushing the air faster, and this is resisting as it goes forward. So this is literally how a curved ball works. Does that make sense, Gabby? Good. What other questions would you guys like me to go through? All right. Okay. Moment of inertia, so radius of gyration. If the mass of the object is 10 kilograms and the length of it is 1 meter from the axis. Okay. So actually, I don't have the moment of inertia here. Give me 1 second. Actually, I do. I'm not being very smart. It's the inertia is going to equal our mass times our radius squared. So when we come here again, it's simply going to be 10 times 1 times 1. Okay, 21. We already did 21. Okay. Wave drag increases by a factor of 1. how much did the athlete's velocity increase? Okay, so here is our drag formula. So if the drag increased by a factor of 1, okay, that means our velocity, since velocity is squared, it needs to have increased by the square root of 1, effectively. Yes. Yeah, protein is not a contributor to bone mineral density losses. That is a red herring that has been decisively debunked through Jose Antonio's work and otherwise. There's a reason why I never talked about it in the lecture, because the book is a bit older and it is wrong. Just like how proteins does not kill your kidneys. Once again, mostly undone by the work of Jose Antonio and his lab. Yeah, the big thing with, they thought more of the idea of taking protein would put you into more of an acidic environment, which naturally would go ahead in theory and cause you to have to donate calcium in order to maintain the acid base balance of the body. It just doesn't work out like that. In fact, protein is important because it's important in the collagen matrix and just overall ability to lay down the bone mineralization in the first place, but nowhere near as important as just calcium, vitamin D, vitamin K, and magnesium for our ability to make sure that we're going to go ahead and keep that calcium there. Now, one thing that I haven't spoken to in the class, and it's a little bit beyond what's necessary here, and we talk about it more in bioenergetics, which is when it comes to tendon and soft tissue, so ligament repair, it's important to understand, A, we don't have circulation to them, so they're naturally going to repair much more slowly than obviously your muscles are, because they're going to be essentially well vascularized through a lot of capillaries, delivering obviously not just your blood, but delivering nutrients and removing waste products very rapidly. But additionally, if we're trying to repair those tendons and ligaments faster, we need to A, move them so that we're going to essentially get some nutrient turnover and allow those areas to repair. But the second thing we need to do is we need to make sure that we're applying the appropriate nutrients. And that's where supplementation potentially with things like collagen protein is going to be very useful as a means to help with that recovery a little bit faster, because literally collagen protein has a slightly different amino acid makeup than eating something like your typical, animal-based proteins or even plant-based proteins. So collagen protein is going to be higher in proline, hydroproline. I don't think serine. Maybe glycine is going to be the other one that are going to be pretty important and useful in helping turn over those tissues faster. And then Seba, correct. What other questions would you guys want to go ahead? It's okay, guys, if you don't have any more questions you guys want to go through. Make sure that you guys are linking up with your groups and that you guys are getting your videos done and working on those wonderful papers along with, remember, we have other assignments of where you're going to have to make sure that you're showing effectively what are going to be the muscles being utilized in what movements. Make sure that we're keeping in mind the difference between an eccentric, concentric, and isometric contraction as we're doing these exercises. So, okay. Do you remember what the question is? Okay, so yeah, question 6, there's your full answer to it in case you're wondering. Okay, so yeah, there's no math separate. So you just have an individual version of the final you're going to take and then the group version of the final you're going to take. Yeah, so that's going to be the different muscles of the spine that are going to go ahead and get you to move in whatever directions we're looking for. So it's probably the ones going with the cervical spine, and that one was very tricky. I will be the first to admit it. So yeah, so cervical flexion is going to be caused by the rectus capitis lateralis and the longus capitis. Lumbar flexion, now we're talking about internal, external obliques and the rectus abdominis. The lumbar rotation, remember, it's going to be the internal and external obliques, and it's going to be the external on one side, internal on the other. That's going to be pulling us when we're going to the right, and then going to be the opposite when we're going to the left because of the way the pennation of those muscles are. And then as far as lumbar extension, that's going to be our iliocostylis and quadratus lumborum, along with our interspinalis and semispinalis. Rock and roll. What other questions you guys got? So obviously, I'm literally just pasting in the exact way that the question is posed. But what's going to cause this increase? Well, it's going to be increased loading, then amplitude. So anything that's going to really cause us to deal with impact. So remember, it's going to be the pennated fibers that's going to give us a greater amount of force production. That's going to be when they're pulling effectively in the angles. And then the linear is going to be the fastest one because it's going in that straight line. We don't have to worry about any of the changes in force production. So that's going to be the semimembranous, tendinous, and then the long head of the biceps femoris. This is going to be the Golgi tendon organ. Now, the exact opposite of this is the muscle spindle, which detects stretch on the muscle and causes it to contract. All right, what are the components of skeletal muscle? So I realize I'm just telling you guys what the answers are. We're better than that. What do you guys got for me? Now that's what they're made up of, but think about excitability. Yes. Exactly. Good job, Chris. Mm-hmm. Good work, guys. What other questions you guys want to go ahead and go through? Okay. What is the torque required? So we know we need torque. Okay. Notice here, guys, to accelerate a rotating object, if it starts rotating at 10 degrees per second and increases to 50 degrees per second in 2 seconds. Radius 3 meters and mass of 100 kilograms. So let's come back over to our handy dandy here. Notice, guys, torque equals our inertia times our acceleration, in which we can then put that out the long way of torque equals our mass times a radius squared times acceleration. Okay, so let's break this down. Our inertia equals our mass times our radius squared. Acceleration equals our final vel minus our initial vel, and all that divided by the time it took. So to solve for this first one, that's going to be equal to Well, mass is 100 kilograms, and then our radius is going to be 3. So 3 times 3 is 9. 9 times 100 is 900. We solve for inertia. So now, this example, okay, finishes at 50, starts at 10, and it does so over 2 seconds. So 50 minus 10 is 40. 40 divided by 2 is going to equal 20. So now, to come back up here, we literally have 900 times 20. So 18,000 Newton meters. Anytime. Probably not, Josh. Probably not. It's going to be more of the limiting factors is going to be that calcium along with obviously vitamin D, vitamin K, magnesium. But yes, if we're really trying to think about what could really influence it, think about more along the lines of, okay, what are we missing? What do we not have enough of? That's going to be the thing that's typically holding us back. Okay, 39. Oh, okay. So remember, now we're talking about active and passive insufficiency. Okay, so depending on the positions of our joints, what's going on with our ability to produce force? Okay, so is it going to be active or passive insufficiency when a joint is restricted due to position? Oh, nice. We're at an impasse. Sorry, I'm trying to make sure I pull up the exact slide so we can go through it. Okay, active insufficiency, guys, is when we can't produce force because muscles are slack. Okay, so we're effectively in too short in a position to really create that maximal force that we're looking for. Okay, now it's going to be passive insufficiency. That's where notice restriction of the joints range of motion. That's going to naturally not allow us to produce the same amount of force we're looking for. So as in, you can bring your wrist back further here, but if you try to open your hand, you can't have your hand back as far as you can when you have your fist closed. That is passive insufficiency. right, guys, 10:35. We're going to go ahead and let you guys out a bit early. Now, next week, Tuesday, when we come back, I want you guys to have questions that you try to work your way through and you're not confident in your answers. So you're going to not just put in the chat, here's the question I'd like you to go ahead and show us how to do it, but I want you guys to show me the answers you came up with. So that way we can work our way through and figure out if you got it correct or if you got it incorrect. And that's fine, because remember, the goal here is to learn. So obviously, you know, you maybe made one little mistake with your math or one of the steps, and that's perfectly fine. So we can hopefully go through there and figure out what's going on. Because obviously I wrote the test so I can answer all the questions and kind of burn through it pretty quickly. Instead, what we're looking for with you guys, obviously, is that you can set it up correctly, think your way through it, and obviously, you know, really show you understand the information. So come with the questions. I really appreciate you guys showing up. Don't disappear right now. I'm going to do kind of well, hold on for a second. Okay, two things. Do this, reopen that. I'm going to go ahead and get to where I can see what's going on the screen. I've got Blackboard pulled up on my other screen. Let me go ahead and hit pause on recording. Yeah, without further ado, guys, stay safe out there. Remember, come with your questions that we can work through, obviously, from the study guide on, on Tuesday of next week. So stay safe, and I will see you guys then. Okay, so bye-bye.